In this lesson, we'll look at applying Schrodinger's wave mechanical model of the atom by arranging electrons in the space outside the nucleus that we call the electron cloud. So this video is intended to address how electrons are arranged in the electron cloud and to show methods that chemists used to represent those arrangements. So using the electron configuration model developed by Schrodinger's model, we have, first of all, what is an electron configuration? An electron configuration is a way of showing how electrons are arranged. This says it's a diagrammatic representation of the arrangement of electrons in an atom. It can be a drawing, such as when we do things like we draw a nucleus, and then we have first energy level, second energy level, and we say we have 2 electrons here and 2 electrons here. That would be an electron configuration of sorts, but this would be using the Bohr model, and this isn't appropriate with the newer model. There are certain rules that we have to consider before we actually try to arrange electrons according to the Schrödinger model. And those are the off-bow principle, Hund's rule, and the Pauli exclusion principle. The off-bow principle states that occupy the lowest energy position available in an atom. So we're always going to start with the lowest energy, and we're going to build our atom by adding electrons to higher and higher energy values. Hund's rule states that orbitals of equal energy are each occupied by 1 electron before being occupied by a second electron. Where this becomes important is places especially like p sublevels, which have 3 p orbitals. And each of these orbitals in a given sublevel would be considered equal in energy. And if they're equal in energy, each one of them is going to be occupied by a single electron before electrons start pairing up. The same would be true for orbitals in d sublevels and also in f sublevels. But in s sublevels only have 1 electron orbital, so they can only have 1 electron and then a second electron. So it doesn't really apply to S. For the Pauli exclusion principle says each electron in an atom has a unique set of 4 quantum numbers. Where this becomes important is when we have 2 electrons that are occupying the same energy level, sublevel, and orbital. They have to have opposite spins. So for instance, for hydrogen, its 2 electrons are in the first energy level, in the s sublevel, and in the s orbital in that 1s sublevel. So the first 3 quantum numbers out of the 4 are going to be the same, but the 4th quantum number, spin, the 2 electrons sitting in this s orbital will have a positive 1/2 and a negative 1/2 spin. We'll apply these as we go, but these are the fundamental rules. Okay. The electron configuration notation that we have, instead of drawing diagrams, we use a notation style. So we write for an electron configuration for an atom is going to look, well, let me show one as an example. We may have an electron configuration that looks like this: 1s2, 2s2, 2p3. This represents the electron arrangement for an atom. So what we need to know when we look at something like this is, what does the number and the letter and this, the superscript represent? Okay, so we have electron configurations to take the notation of n, x to the y. This is not a mathematical notation, so to speak, although it looks like it. Okay. N here is the principal quantum number. This is the energy level where the electron is going to be found. X is the sublevel that contains the electrons. That can be S, P, D, or F, depending on the electron. And then Y represents the number of electrons in the sublevel. And it's important to know that S can hold up to 2, P up to 6, D up to 10, and F up to 14. These are max numbers. You can't have less than that. So important things to remember when you're trying to put together electron configurations: the number of available sublevels equals the energy level number. We've seen some of this in some of the work that we've done thus far. So energy level 1 has 1 sublevel, 2 has 2 sublevels, 3 has 3 sublevels, and so forth. We also need to know the number of electrons that fit into an energy sublevel. Again, S holds up to 2, P up to 6, D up to 10, and F up to 14, max. We also need to know that electrons are added according to the Aufbau principle and Hund's rule. In the first type of notation, we're going to pay special attention to the Aufbau principle. In the second type of notation that we'll add to it, we'll have to pay special attention to Hund's rule as well as the Aufbau principle. So what we need to know here is the energy order of the energy levels and sublevels. And we'll have various ways to be able to sort that out. Okay, so let's start with an example. Another piece of information that you must know about the individual atoms is the number of electrons. The number of electrons for an element is the same as the atomic number, Z. Atomic number for hydrogen equals 1. Now, we also can look at hydrogen's location on the periodic table. If you have a periodic table out, you will find that hydrogen is on period 1 of the periodic table. The period on the periodic table means that of the first energy level will be needed. We can also say that the first energy level will be the highest occupied energy level. And of course, the period number is actually the principal quantum number. For the highest occupied energy level. So we know we're going to need 1 energy level. Okay, so we have an atomic number of 1, there, which means 1 proton. That means we have 1 electron. So we're going to start by placing this 1 electron in the lowest energy level possible, which is energy level 1. So we write a 1 for the energy level. We then have to place it into a sublevel. Energy level 1 has only one sublevel, which is S. So we're going to place the one electron in the S sublevel. An S sublevel can hold up to 2 electrons. We have 1, so this S sublevel can hold all that we have. So we place that 1 electron as a superscript. So this is read as 1s1, but what it means is first energy level, S sublevel, 1 electron. That's the total electron configuration for hydrogen. Let's try another. Helium, we have an atomic number equal to 2, meaning that we have 2 electrons that we have to account for. Also, keep in mind when we do these, in general, we're looking at ground state. Okay. So we start with our electron. We're going to start putting electrons in the lowest energy level. That would be 1. In the lowest energy sublevel, and only sublevel in energy level 1, we have S. Every electron configuration is going to begin with 1s, because that's always the lowest energy level and its single sublevel. We then know that S sublevels can hold up to 2 electrons, and therefore we have 2 electrons, so we place 2 there. 2 will fit in the S sublevel. Final electron configuration for helium. Next, lithium. Lithium has an atomic number equal to 3. So we start with energy level 1. We start with its S sublevel, and we can fit up to 2 electrons in 1s. We have 3 total that we have to account for, but we all have used 2 here, so we then have to go to the next location. There is no other sublevel in energy level 1, so at this point we can say here we have a full first energy level. So from there we have to go to the next highest energy level, which is 2. In energy level 2, we have a choice of either S or P sublevels. S is always going to be lower than P, which is lower than D, which is lower than F in energy, as long as the energy level is the same for all of them. So in energy level 2, S sublevel is lower in energy than P sublevel, and according to the Aufbau principle, we place the electron in the lowest energy sublevel. And we have 2 electrons here, we only have 1 left. S will hold up to 2, so it will hold our 1 electron to give 2s1. So we have 1s2, 2s1 as the electron configuration for lithium. Next is carbon. Carbon is Z equals 6. So like all of our atoms, we start with energy level 1, S sublevel, and we know by this time we can fit 2 electrons in it. So 1s2. That leaves 4 electrons. We then go to 2s. 2s can also hold up to 2 electrons, as any s orbital can, or s sublevel can. So we have 1s2, 2s2. 2 plus 2 is 4 electrons. We still have 2 electrons left. S is full, but S, remember, has, energy level 2 has an S and a P sublevel. We've used the S. Next we go to 2P, and we can fit up to 2. We can actually fit up to 6 electrons, but we only have 2 available, so we place both of them here. So 2 electrons in the 1s, 2 electrons in 2s, 2 electrons in 2p to give 2, 4, 6 total electrons. This is carbon's ground state configuration. Next we have neon. Z equals 10. And with 10 electrons, we have 1s2, that leaves 8. Then we go to 2s, 2, that leaves 6. We go to 2p. P holds up to 6 electrons. We have 6 left. We place all 6 in there. At this point, we have a full first energy level, and we also have, at this point, a full second energy level. Remember that the first energy level can hold up to, first energy level, 1 squared is 1 times 2 is 2, 2 electrons in the first energy level. Second energy level, 2 squared is 4 times 2 is 8, 6 plus 2 is 8 electrons. Our last one that we're going to do as an example is aluminum. Aluminum has 13 electrons, so this is Z equals 13. And with this, we're going to have 1s2, 2s2, then we go to 2p. 2p can hold up to 6. We got 6, 7, 8, 9, 10. We still have 3 electrons left. This is a full first energy level. This is a full second energy level. So now we have to go to the third energy level. Note with aluminum that it's on period 3, so that tells us we're going to need at least 3 energy levels. We start with 3s. 3s can hold up to 2 electrons. We still have 1 left over, so that means we go to 3p. Remember that energy level 3 can hold, has sp and d orbitals, sublevels present, and we're going to utilize the p for 1 electron. So that gives 1 plus 2 is 3, plus 6 is 9, 10, 11, 12, 13 electrons. Final electron configuration for aluminum. Now I'd like for you to try some. We have oxygen, phosphorus, magnesium, fluorine, argon, and potassium. I'm expecting to be able to see these in your notes that you upload to Northside Science, and the answers to these will be discussed in class. Please pause the video now or stop the video, but make sure that you have these problems written down and solved in your notes.